Okay, welcome everyone to IIT Bombay Virtual Competitive Algebra Seminar. We are very happy to have Laxmi from Tata Institute, and today she will speak on Gorenstein rings of codimension 4. Over to you, Laxmi.
Thank you. Thank you for giving me opportunity to present my work. So I'm going to talk on structure of codimension 4 Gorenstein rings. So here we will study the structure of grade 4 Gorenstein ideals using free resolutions. So in the first part of the talk, we'll see existence of Spinor structure on resolutions of grade 4 Gorenstein ideal, and also we'll see several examples of grade 4 Gorenstein ideal with the Spinor coordinates. In the second part of the talk, we will see construction of grade 4 Gorenstein ideals using doubling of grade 3 perfect ideals, and this construction gives almost this construction of from the grade 3 perfect ideals gives almost all known grade 4 Gorenstein ideals. So before getting into the theorems and results, I define the notations and the notations used throughout the talk. So here R is, we assume R always to be commutative Noetherian ring, and I is an ideal here. We say ideal I is perfect if grade of I is same as the projective dimension of R mod I over R. I is Gorenstein ideal of grade G if I is perfect, and the gth x of R mod I comma R is cyclic as an R mod I module. So as I mentioned earlier, so we are going to study structure of grade 4 Gorenstein ideal via free resolutions. So finite free resolution is a sequence of module Fi with the maps differential Di, such that the sequence is exact and each module Fi is free. So in order to study the Spinor structure on codimension 4 Gorenstein rings, we use result of Buchsbaum and Eisenbud structure theorem. So in order to see that that structure is a generalization of a consequence of Hilbert-Bers theorem. So Hilbert-Bers theorem is for the grade 2 perfect ideals. It says that the resolution of R mod I is of this form, where this Y is n plus 1 by n matrix, and X is 1 by n plus 1 matrix, where entries of X matrix xi are the minus 1 raised to I a times delta I, where a is a non-zero divisor and delta I is n by n minor of matrix Y with ith row deleted. Note that in this case, the rank of X is 1 and the rank of Y is n. So that by the rank nullity theorem, we can see that the rank of X plus rank of Y is n plus 1. So that gives an isomorphism from Rn plus 1 is isomorphic to the nth exterior power of Rn plus 1 star. Yet star denotes the R dual. So as a consequence of this existence of non-zero divisor by the Hilbert-Bers theorem gives the factorization of map X. So X comes from the previous resolution, that is a map from Rn plus 1 to R, and the isomorphism, as we have seen, there is isomorphism from Rn plus 1 to nth exterior power of Rn plus 1 star, and then we take the dual from Rn to Rn plus 1, and we take the nth exterior power of that map, which gives a map from wedge n Rn plus 1 star to R, and that map is nth exterior power of Y star. And there is a as a consequence of Hilbert-Bers, there is a multiplication map from R to R, and this commutative diagram gives the factorization of map X. So such factorization of and note that the rank of X is 1. So it gives actually the factorization of some exterior power of the differentials. Such result has been generalized for any finite resolutions by Buchsbaum and Eisenbud in 1974. So consider a finite resolution of length n, and then di's are differentials, fi's are free modules, and denote Ri to be the rank of differential di. Then they proved that there exists a unique sequence of homomorphisms from R to kth exterior power of fk minus 1, such that the last map an can be given as the Rn exterior power of Dn, and this diagram commute. So that this diagram, you can see in this diagram, Rk plus 1 is a rank of Fk, and we have that isomorphism, and then and the other maps are the Ak. So here this diagram gives a factorization of wedge Rkth exterior power of Dk. Let's put here k equals to 1. In that case, this keeps the last previous map what we see as a consequence of Hilbert-Burt. So this map AK plays a very crucial role in defining the spinors on codimension 4 Gorenstein rings. So this map AK is said to be Buchsbaum-Eisenbud multipliers map, and the coordinates of map AK we call as the Buchsbaum-Eisenbud multipliers. So we define a term called I. We define IF. For this, we need P and Q are finite Fourier modules, and F is a homomorphism from P to Q of rank R. That is important. Then I of F is a ideal generated by R bar R minor of matrix F. So we use this notation. So the previous theorem which we discussed about the Buchsbaum given by Buchsbaum-Eisenbud, that is also known as the first structure theorem. So by the first structure theorem, if the depth of I of D1 is n, then the radical of I of D1 is same as the radical of I of AK for k bigger than 1. So note that if we talk about the grade 4 Gorenstein ideal, then the Buchsbaum-Eisenbud multiplier are always in the radical of I. And if I is a radical, then the coordinates of Buchsbaum-Eisenbud coordinates, or we can the Buchsbaum-Eisenbud multipliers are in I. So for the structure theorem, for the grade 3 Gorenstein ideals has been classified completely earlier by Buchsbaum and Eisenbud, but for in case of grade 4 Gorenstein ideal is not classified completely. So the first result on grade 4 Gorenstein ideal was given by Kustin and Miller in 1980. So here we assume R is Gorenstein and 2 is unit in R, and I is a grade 4 Gorenstein ideal. Suppose I is minimally generated by an element, and suppose this F is a minimal free resolution of R mod I. Then, because this R mod I is Gorenstein, so canonical module is same as it is cyclic and it's R mod I. So we have this isomorphism F4. We can see that this F4 minus I is isomorphic to Fi star. And by the rank nullity, it can be seen that the rank of F1 is n and rank of F2 is 2n minus 2. So in case of grade 4 Gorenstein, the resolution of grade 4 Gorenstein ideals, the second module F2 is always of even rank. So this is very important property. This is very important property they Kustin and Miller have proved for this. So there exists a symmetric isomorphism S from F2 to F2 star. This symmetric isomorphism in their paper they call it as a dualizing map, and there is also this. They prove that there is isomorphism from F to F2 which is of this form. So map from complex from F to F star is of form where other maps are identity. Only the map from F2 to F2 star is S. So this S induces a bilinear map from F2 tensor F2 to R, and that is non-degenerate bilinear map. And they have given the multiplication map F1 star F1 tensor F1 star to R, that is this evaluation map. And then this bilinear map has this adjoint relation, and because of this adjoint relation, the inner product of image of D3 comma image of D3 is 0. So but in general, the dualizing map S, which is a symmetric isomorphism, it need not be unique. But they have shown that for in case of if we take the complete regular local ring, then that map S is unique, and it is of this form, where it is 0. It is a block matrix where 0 and this I n minus n minus 1 by n minus 1 identity map, and the third block is I n minus 1 and 0. So this form of S is also called the standard form, or what is called we call it as a hyperbolic form. So as we have, as the result says that this S induces a bilinear map, non-degenerate bilinear map. So in case of in case of polynomial ring, recently we have shown that suppose R is a polynomial ring of field K and I is a grade 4 Gorenstein ideal, and suppose I is minimal generated by an element and F is a minimal graded free resolution of R mod I, then we have shown that there exists symmetric isomorphism S, which is in standard or hyperbolic form, we can say. So in case of both, in case of complete regular local ring, or in case of our polynomial ring, S is in the standard form, or we can say in the hyperbolic form. So this both this S over the complete regular local ring or over the polynomial ring, this induces a bilinear map. So bilinear map looks like this. So inner product from this map from F2 tensor F2 to R. Suppose E1 to En minus 1. It is on some ordered basis. E minus 1 to E minus n minus 1. This is the basis for F2. Then with respect to this basis, the bilinear map is defined this way, where any element can be written as summation of ai ei, I from 1 to n minus 1, plus summation of a minus I, e minus I. And so a bilinear map is in this form. We can see that basis of F2 with respect to this bilinear map is called the hyperbolic basis, because it can be checked that the inner product of ei, ej is 0, e minus I, e minus j is 0, and inner product of ei, e minus I is 1. So this, because of this bilinear map, the basis of F2 is divided into two parts. One is the E1 to n minus 1, and other is E minus 1 to E minus of n minus 1. And one part is a dual of the other, what we can say, because of the property of the bilinear map. We call such module F2, which is of even rank, as we have seen earlier, 2n minus 2. With this bilinear map, this is called orthogonal R module. So now there is a concept of orthogonal space for the vector space. Suppose V is a vector space over C of dimension 2n minus 2, and there is a symmetric map from this symmetric bilinear map from V cross V to C, and it's defined in this way. So V paired with this this bilinear map, non-degenerate bilinear map, it is called an orthogonal space of dimension 2n minus 2 over C. And because of the properties of this, by the way it is defined, the bilinear map is defined, this divides the basis of V into two parts, where it is E1 to En minus 1 and E minus 1 to E minus of n minus 1. And here, because an EI and E minus I are of the weights epsilon I and minus epsilon I. So these weights come as a dual of the Cartan subalgebra with respect to this orthogonal, special orthogonal Lie algebra associated with this vector space V. So, so by the classification of semi-simple Lie algebra, this vector space V or even dimension vector space V is associated with linking types Dn minus 1. And this Dn minus 1 has roots alpha I, which is epsilon I minus epsilon I plus 1, and for other, there are other two roots are alpha n minus 2 and alpha n minus 3, n minus 1. So then we can represent those roots from diagram called what is called the dinking diagram. This is of dinking type Dn minus 1, and this diagram looks in this form. So here the two nodes corresponding to alpha n minus 1 and alpha n minus 2, this corresponds to the Spinor representation. So let's see here. So weights corresponding to, so weights omega I from epsilon 1 to epsilon I, and this from I from 1 to 1, this is one weight, and the other weights are omega n minus 2 and omega n minus 1. These are two weights. So the representation, fundamental representation with respect to these weights, omega I, this is we call as a denoted by V omega I. And from I from 1 to n minus 3, this can be given as the ith exterior power of V. For the other representation corresponding to omega n minus 2 and omega n minus 1, these are called the Spinor representations. And dimension of these vector spaces are 2 to the power n minus 2. And it has weight, so V omega n minus 1 has weight half times the plus minus of this epsilon 1 to epsilon n minus 1. So note that in that case, the even number of minuses are there, and for the other case, there are odd number of minuses. So now we are ready to define the Spinor structure on the solution of codimension for Gorenstein ring. So our definition for the codimension 4 Spinor structure on codimension 4 Gorenstein ring is motivated by the result of Miles Reed. The first the Spinor structure on codimension 4 it was used by Miles Reed in 2011. But in our definition, we use Buchsbaum-Eisenbud multiplier to define Spinor structure on codimension 4 Gorenstein resolution of codimension 4 Gorenstein rings. So here, suppose R is a complete regular ring over field C, or it is a polynomial ring over C, and where 2 is in region R. Suppose I is a grade 4 Gorenstein ideal, and I is minimally generated by an element, and F is a minimal free resolution of R mod I. Then we say that this F has Spinor structure if there exists a map A3 delta from R going to the half spin representation tensor with R, such that the Buchsbaum-Eisenbud multiplier A3 can retain a composition of second symmetric power of A3 delta with map P. P is certain map we have defined in our work. So this the map this A3 delta is called the Spinor map, and the coordinates of this are called the Spinor coordinates. So this relation of the A3 as a second symmetric power composed with P, this gives a very nice relation between the Buchsbaum-Eisenbud coordinates, the Buchsbaum-Eisenbud multiplier, and the Spinor coordinates. So, so in my joint work with Seligpas and Weiman, we have proved the existence of Spinor structure for resolution of codimension 4 Gorenstein rings. So here we have proved over any algebraic closed field, but here I mention over the complex. So here RMC is a complete regular ring.
Laxmi, sorry to interrupt you. Is it really essential to restrict over complex field?
No, for complex it is easier to see the fundamental representation. We have proved it for linking type Dn is we can talk about over any algebraic closed field the representation for what we are talking about this because in that case the second decomposition of second symmetric power of half spinor representations are even true in case of if we take algebraic closed field. So
it can be characteristic 0 or P or whatever, but it should be algebraically closed, you are saying.
Yeah, it should be algebraically closed. Yeah.
Okay, thank you.
So we have proved the existence of Spinor structure on resolution of codimension 4 Gorenstein ring, and this existence of Spinor structure gives very nice relation between the Buchsbaum-Eisenbud multiplier and Spinor coordinates. It gives a quadratic relation between the Buchsbaum-Eisenbud multiplier and Spinor coordinates. For some relations we will see further in the talk. So so let's now realize let's relate the first structure theorem and the resolution of the relation between the differentials of the codimension 4 Gorenstein ring and Buchsbaum-Eisenbud multiplier. How can we relate that? So as we have seen earlier, as a consequence of the Kustin-Miller result on the codimension 4 Gorenstein resolution of codimension 4 Gorenstein ideal, we had a very nice isomorphism between the resolution isomorphism between the F and F dual. So that helps us in determining the resolution. So it is enough to determine the D1 and D2, and that determines half of the resolution for codimension 4. So we can get D3 and D4, and D3 is S times D2 star, and D4 is D1 star. We can write in that form. It is one more thing is that this existence of this S, what is in the hyperbolic form, divides the differential D2 into two parts. So one part we can denote as a hyperbolic basis E1 to E, and we can say we can denote it by columns. We can write it as 1 to n minus 1, and other we can denote as minus 1 up to minus n minus 1, because existence of this map S, we can do that. So now by the first structure theorem, there is an n minus 1 exterior power of S times D2 star with indexing set K can be written as A3K D1. So A3K is a Buchsbaum-Eisenbud multiplier, and this so we can always relate this. We can always find this A3K from this minor n minus 1 by n minus 1 minor of S times D2 star. So so now using what we have discussed now, there is a relation between the Buchsbaum-Eisenbud multiplier and the Spinor coordinates. So we choose the indexing set K to be minus J union J complement. Here minus J denotes the columns of D2 which we choose as a minus. because of the existence of hyperbolic forms, we can divide the D2 into two parts. So some half part corresponds to the minus column. We take J to be indexing set in 1 to n minus 1. And then for even number of element in J, there's a relation that the Buchsbaum-Eisenbud multiplier with respect to indexing set K, where K is a minus J in J complement, that is the square of the Spinor coordinates corresponding to the indexing set J. For the odd cardinality, this Buchsbaum-Eisenbud multiplier corresponding to that indexing set is 0. So it is always true. It is always like for even if sometimes it is for the even cardinality 0 or sometimes it is for the odd cardinality 0. Both is not possible. So other property is that as we have seen already earlier that the Buchsbaum-Eisenbud multipliers are element of R, and we assume that R is either complete regular local ring or polynomial ring. So in that case, the Spinor coordinates are forced to be the element of R because it is a normal domain, so it is forced to be in the R. As a consequence of the previous what we have, the relation between the n minus 1 exterior power of the S times D2 star, we have this relation for the indexing set K equals to minus J in J complement. We can write this relation. Other thing is that the Spinor, because the Buchsbaum-Eisenbud multiplier are always in the radical of ideal I in case of grade 4 Gorenstein ideal. So that forces the Spinor coordinates to be also in the radical of I. And if I is a radical ideal, then Spinor coordinates are in I. So now we'll see several examples of grade 4 Gorenstein ideals. Several examples of Spinor coordinates in the grade 4 Gorenstein ideal. We'll see that. So first we start with the Kuzel complex. So note that here we don't, in the case of Kuzel complex, we don't put restriction on the R because everything we put restriction on the ring as a consequence of the existence of this hyperbolic basis. For the existence of hyperbolic basis, we put all the restrictions on the ring. So here we take R to be any Noetherian local ring, and we resolve this resolution on identity of x1, x2, x3, x4. So resolution is of this form, where F2 is second wedge product of R4, exterior power of R4. And the differential D1, D2 are of this form, and the symmetric isomorphism S is this. Now here, note that what we can say this symmetric bilinear map is simply the exterior product. It is just that product is simply the exterior product here in case of Kuzel complex. And in this case, we can write the columns as 1, 2, 3, and minus 3, minus 2, and minus 1. And we take indexing set accordingly. So compute the Spinor coordinates here. Suppose take J indexing set in 1, 2, 3, and take J to be empty set first. Then the Buchsbaum-Eisenbud multiplier corresponding to K, what we had, minus J is empty. J complement is 1, 2, 3, and that corresponds to plus minus x4 square. And similarly for J, if consists of I comma J, then that gives another Buchsbaum-Eisenbud multiplier. So the Spinor coordinates are simply the square of this Buchsbaum-Eisenbud multiplier, and we can see that the Spinor coordinates we can get all the Spinor coordinates from differential D2. One more thing is that the Spinor coordinates are here. All the Spinor coordinates are among the minimal generating set of the ideal. So this is only possible for the complete intersection, that all Spinor coordinates are among the minimal generating set of the ideals. One more thing I forgot to mention in the theorem, that as a consequence of theorem, that if we know this, if we find the Buchsbaum-Eisenbud multiplier for indexing set of the form K equals to minus J union J complement, it is enough to get Spinor coordinates for that, because other Buchsbaum-Eisenbud multiplier can be defined the quadratic relation with this Spinor coordinates only. So here. In this case, this property of this Spinor coordinates classify the complete intersection in this form, which is not true for if we go to a higher number of generators of the grade 4 Gorenstein ideals. So now we go for the higher generator. So for this we use this grade 3 Gorenstein ideal. As we have the grade 3 Gorenstein ideal, the ideal can be given as generators of the ideal comes from the submaximal ideal generator submaximal Pfaffian of certain skew symmetric matrix, which is given by Buchsbaum-Eisenbud. They prove that, and any resolution of R mod J is of this format. By the choice of basis, we can make the X to be skew symmetric matrix, and the differential partial one that we can say is of this form. So for using this grade 3 Gorenstein ideal, we can get grade 4 Gorenstein ideal by taking tensor of these two. So we take extra variable y, and we tensor, and we take the polynomial ring over C with entries from x and additional variable y, and we take tensor of these two complexes, and this gives us grade 4 Gorenstein ideal. And so we talk about the Spinor coordinates here. So in this case, we need the second differential d2, which is from second differential d2 is from r2n plus 1 direct sum r2n plus 1 to r direct sum r2n plus 1, and which is a block matrix. Now we use this differential d2, and then we divide into the hyperbolic basis form, and we find the Buchsbaum-Eisenbud multiplier, which is in this form. Now note that here, if we choose the indexing set of J to be 2n, the correlative, the number of element in indexing set to be 2n, then the Spinor coordinate is forced to be the Pfaffians, which is a sub-maximal Pfaffian, which is generator of which are among the minimal generating set of the idea. So in case of and this example, what we call as a hyperplane section of Pfaffians. So in case of hyperplane section of Pfaffian, except one, all the generators are among the Spinor coordinates. So in case of completed section, we have all generators were among the Spinor, minimal generators were among the Spinor coordinates. Here, except one, all the generators are among the Spinor coordinates. Note that if we take n to be 2, then we have grade 3 Gorenstein ideal is of the form 1, 5, 5, 1. And the hyperplane section of Pfaffian gives 1, 6, 10, 6, 1. And the only known example for the 6 generator grade 4 Gorenstein ideals are the hyperplane section of Pfaffian. So we know the Spinor coordinate for this all the known grade 4 Gorenstein ideals. So now next is we talk about the Spinor coordinates of grade 4 Gorenstein ideal with the 7 generators. So the such 7 generator example was given by Kustin-Miller, and they associated this example with a 3 by 4 matrix, a 4 vector and a variable, and and they consider a polynomial ring R over C with these entries from this matrix and extra variable y, and denote Qi to be this. Then the ideal, they give ideal looks in this format, where M1, 2, 3, 2, 3, 4, these are the 3 by 3 minor involving first, second, third row and second, third and fourth column, and similarly other. So, and the resolution for this I is of the form 1, 7, 12, 7, 1. So here, note that this in their work, they have given this name as a construction of big Gorenstein ring from the smaller one. So they used two Gorenstein, one grade 3 Gorenstein ideal, and other they use the grade 4 Gorenstein. They use 1331 and 14641 to construct the Gorenstein grade 4 Gorenstein ideal with the 7 generators, and they call it as a Kustin-Miller Unprojection. We call it as a Kustin-Miller Unprojection family. This gives a family of ideals, a family of ideal grade 4 ideals. So in this case, we have so matrix D2 is very huge, so I have not written that. So in this case, we do same thing. We divide D into 2 parts, depending on the hyperbolic basis, and then the Spinor coordinates are recorded here. So for up to the J, if we take J to be singleton 1, or up to, we can see up to the 4 columns or 4 rows, we can see that Spinor coordinates are linear combination of the minimal generating set of the ideal. For the other 4, they are among the minimal generating set of the ideal. So either in the 7 generator case, 4 of the Spinor coordinates are among the minimal generating set of the ideal, and other are all a linear combination of the minimal generating set of the ideal. So here in this this 7 generator was only the known family. This family was the only known family for grade 4 Gorenstein ideal with the 7 generators. And Miles Reed asked whether every family coming from this 7 by 12 matrix with grade 4 Gorenstein ideal with the 7 generators comes from this or a specialization of this Kustin-Miller Unprojection. So later on, we have given an example which is not specialization of this family coming from this unprojection family. So till now, we have seen all the examples where at least one of the Spinor coordinates are among the minimal generating set of the ideal. So this Spinor coordinates, and there's a property, there's a behavior of the Spinor coordinates being the minimal generators in each example we have seen. But this is the first example for the 9 generator grade 4 Gorenstein ideal, in which none of the Spinor coordinates are among the minimal genetics of the ideal in this case. This 9, so we consider 3 by 3 generic matrix, and we consider 2 by 2 minor, ideal number 2 by 2 minor of this X. And this resolution of this complex is called what is called Gulliksen-Negard complex. In this case, by the degree comparison, we can see that the Spinor coordinates are of degree 3, whereas the minimal genetic set of the ideal are degree 2. So this forces Spinors to be the Spinor coordinates to be the linear combination of the minimal generators of the ideal. So this behavior, this Spinors classifies classifies the grade 4 Gorenstein ideal with the 8 generators, up to 8 generator and 9 generator onwards. The behavior of the Spinor coordinates are different. So till now we have seen several examples of grade 4 Gorenstein ideal with the Spinor coordinates. Now in the next part of the talk, we'll see the construction of grade 4 Gorenstein ideals using grade 3 perfect ideal. So I said the notations here. So we start with the local ring Q, where 2 is unit in Q and J is a grade 3 perfect ideal. The minimal resolution of Q mod J is of this form, where we set rank of F1 is N, rank of F3 is T, and rank of F2 is N plus T minus 1, we can say by rank nullity. Then because J is perfect, so canonical module of Q mod, I should write Q mod I, is X3 of Q mod J, comma Q. And also because Q mod J is perfect ideal, so the dual of this complex F gives the resolution for the canonical module, and by sign convention we write a minus of partial. And this star denotes the transpose. Partial 2 star is the transpose of partial 2. So, so first thing is we need to get the injective map from the canonical module of Q mod J to Q mod J, and one of the conditions for this getting existence of this injective map, that means the canonical module is identified with an ideal of Q mod J. That Q mod J is a generically Gorenstein, then canonical module of Q mod J can be identified with an ideal of Q mod J. And in case if the canonical module is a proper ideal of Q mod J, then the quotient ring Q mod J mod the canonical module is the grade 4 is a codimension 4 Gorenstein. So its projective dimension is 4. So now if we assume that it's generically Gorenstein, then we have the injective map. But by some modification, we can always, it is enough to know the injective map psi from canonical module to ring itself, and psi naught and psi 1, and other we can just, it is a transpose of psi 1 and psi naught. So so now we define what is called doubling construction. So the mapping cone, if we take the mapping cone with respect to this psi map, injective map psi, if there is injective map, and this cone of psi, what we call as a doubling construction, doubling of Q mod J. So, and note that here the cone of psi has differentials of the form D1, D2, D3, D4, and this is exactly what we form the existence of the S map, which is in hyperbolic form. So D1, actually D4 star is a D1, and D3 star is a D2 composed with S. So here we can talk about the Spinors in this case, because S is already in hyperbolic form. So, but our what we want is what is called generic doubling. So this is what is generic, in this case generic doubling. Here we take the minimal generators of the home module, dual of the canonical module. Suppose F1 to FL are the minimal generators of the canonical module, and what we attach those many variables to the ring Q, and we take a bigger ring, and in that we take psi to be the combination of tau I and Fi, and this psi is injective map, and then we can talk about the mapping cone construction. And such construction of mapping cone, we call it as it is obtained by generic doubling. So let's see example of generic doubling. So we see here, in this case, we see generic doubling obtained from grade 3 Gorenstein ideal, and we know that can be that is a submaximal Pfaffian of certain skew symmetric matrix. And this is Gorenstein, so there's the home dual of the canonical model is just identity map, one generator. So we can attach a variable y, additional variable y, generic variable y, and we have this ideal I, which is of grade 4. And the resolution of this, it can be checked that the resolution of Q mod I is of this form. So in this case, if we take n equals to 2, then we can get the hyperplane section of Pfaffians, so that is 1, 6, 10, 6, 1, is obtained by the doubling of 1, 5, 5, 1. So means all known example with the 6 generator, grade 4 Gorenstein, can be obtained by doubling of grade 3 perfect ideal. So next, what we see as a construction of explicit construction of doubling for certain class of ring. So what we see as for the almost completed section of grade 3. Structure of such structure for the almost completion grade 3 was earlier studied by Anne Brown, and I use this. I use the construction of this structure of Christensen, Variation, Weiman to construct generic doubling for the grade 3 perfect ideal. So K is a field, and we consider two vector space F and G, and we define the ideal with the help of this Q, n plus 3 by n plus 3 cross n plus this Q symmetric matrix T. It is a block matrix where this U 0, first block is 0, second block U is 3 by n matrix, and the C is n by n matrix. And then we have the ideal for the odd case and even case. We have different ideal. For the even case, we have it has 4 generators. So Pfaffian of T, Pfaffian of 1, 2, 1, 3, and 1, 4. So this 1, 2 denotes the first and second row and column omitted. The Pfaffian of T with the first and second rows and columns omitted. And for the odd case, they generated ideal by Pfaffian of 1, 2, and 3, and 1, 2, 3. These ideals also come from the Schubert variety. So as they have in their paper, they have worked on that. So this Jn is they have shown that this Jn is a grade 3 almost complete intersection perfect ideal. And other thing is that this Q mod Jn is a normal domain. And they studied the structure of these resolutions for the Q mod Jn. So for odd even case, they gave this the first structure, first resolution, and for the odd case, the second resolution. So we use this resolution to construct explicitly generic doubling for this rings. So first condition is that we need to show that this Q mod Jn is generically Gorenstein in order to construct embedding or injective map from the canonical model of Sn to Sn itself. So by the result of the Matsuoka 1977, so there exists homomorphism phi n from canonical model of Sn to Sn such that the sequence is exact. And then Vasconcelos and Simis, they have proved that this Sn is generically Gorenstein if there exists such kind of sequence which is they exist by the Matsuoka result. And they also say that this Sn has to be Cohen-Macaulay. In our case, it is Cohen-Macaulay. So that this shows that this Sn is generically Gorenstein. So now we are ready to construct injective map from the canonical model of Sn to Sn itself. Now how to construct that map? First thing is that it's a mind observation that the dual of the canonical module with Sn dual can be viewed as a kernel of this partial 3 tensor with S. It can view as a kernel of this. So using in order to get this kernel, these are the generators. Which this is not. We will see these are the n of generator, but for this this generator, suppose we consider a module H2m generated by image of these two maps. So first map is a wedge 2mf tensor with G going to F tensor wedge 2m minus 2f tensor with F tensor G. So this map is actually it is a composition of the simply it is a composition of diagonal maps where this wedge 2m minus 2 and F tensor G are identified as sub-representation of Q. Similarly, we have the second map. So the image of these two maps, module generated by image of these two maps are contained in the H2m dual of this home. And also, it is shown that this H2m, the module H2m, is actually the image of the module image of the phi map given by Matsuoka. Similarly, it is shown for the odd case that the image of these two images, the module generated by image of these two maps, where first one is wedge 2m plus 1f going to f tensor wedge 2m. It is just the image of diagonal map. And the second map, the image of these two maps generate the S2m plus 1 dual of the not generate, will say contain in that is image is contained in the S2m plus 1 dual of the canonical module. So, but we need all the generators. So, for that we use this thought exact sequence, which is given by Matsuka, and then we show that if we apply home dash Sn to this thought exact sequence, that is exact. And second thing is that the omega Sn dual of omega Sn is the image of phi and transpose of phi n. That is the other thing. And then as a consequence of these two, we show that the Gn mod Gn square is a reflexive Sn module. So, so we use this sequence. First, we show that for the prime in the associated prime of Sn or for primes with height less than 1, we show that this Schrodinger sequence is split exact. So, for if P is an associated prime of Sn, then Snp is complete intersection. And this if Snp, if it is Sn, as we have seen already, Sn is normal domain. That means Snp is a regular local ring for primes with height less than or equal to 1. So, in both the cases, this Schrodinger sequence is split exact because this canonical module is free and Jn mod Jn square also free. Localized at P is free. So, but we need the generators of the home. For this, we use the resolution for the Sn, which is of the form 1, 4, n plus 3 n. So we can write in terms of Q. So it is of the form 1, 4, n plus 3 and n. And what we do in this, we apply the home R dash Sn to this, and we get the below exact sequence we get, where the kernel of partial 2 prime is just home Sn of Gn mod Gn square comma s. Now, as we have, so we can using that sequence, we can get this Schrodinger sequence, and also it can be checked that partial 2 prime is just transpose of phi n. That means the image of partial 2 prime is contained in the omega Sn dual of omega Sn dual of omega Sn. So for the prime associated primes of Sn or primes with height less than 1, the image of partial 2 prime is isomorphic to omega star Sn by this. For other primes, we know that this by the sequence we see that Jn mod Jn square star whole star is the third CZ module. So this image of partial 2 prime is second CZ module, and by the result of the Fox-P, this associated prime of image of partial 2 prime is contained in associated prime of S, and this depth of the image of partial 2 prime is bigger than or equal to 2, minimum of 2, and depth of SNP. So we have already for the height P less than 1. So for P, so for any prime of Sn, either one of the condition holds. The first condition, as we have already seen for the associated prime or height of P less than 1, or the second condition, either this holds. So, if these two conditions, one of the condition holds, then it can be done that the dual of the canonical module is same as the image of the phi n star. So we have the generators for the canonical module, and it has 4 number of minimal generated by 4 elements. We can say that, and as a consequence of this, we can say that we have this do a home if we apply home on the Schrodinger sequence given earlier, then this is exact. And by the Matsuka result, canonical module of Sn is reflexive, and then also Gn mod Gn square is torsion free as an Sn module. And using above exact sequence, it can be shown that Gn mod Gn square is reflexive as an Sn module. So now we know the generator of the generator of the home module. So what we do, we take the 4 generators, and and we attach those number of variables to, and we take the bigger polynomial ring, and we have the map psi n with summation of alpha hi. So we have the map from the canonical module of Sn to Sn. I should write Sn tilde there, and that using that map, injective map, there is a mapping cone construction, and that is generic doubling, what we call. It is of the format 1 n plus 4, 2 n plus 6, n plus 4 n 1. So let's see an example. So for n equals to 3 case, that means we consider the almost complete intersection with the resolution 1, 4, 6, 3. In that case, we know that home is always generated by, it has 4 minimal generators, and we attach 4 variables there. And J3 is a almost complete an ideal at 4 generators. It is of this form. And generator of the home is given by 3 by 4 matrix. And we take the generic combination, then we can get S1, S2, S3, S4, sorry, S1, S2, S3, and we have the ideal I3 there. As a construction of this, the doubling construction with respect to map, injective map, we have a resolution which is of the form 1, 7, 12, 7, 1, which is generic doubling of 1, 4, 6, 3. We have shown that this deformation of this generic doubling, the deformation of this I3 ideal, gives the resolution which we have seen already in the construction of Kustin-Miller Unprojection. So that was only known family, and so this deformation of this generic doubling gives Kustin-Miller family. So doubling gives even almost all known give all known 7 generator grade 4 Gorenstein ideal. So, but yeah, this is the family I was talking about. The deformation of that I3 gives this Kustin-Miller family. And other thing is that if we don't take a deformation, then it is what the generic doubling we constructed. It is a specialization of the Kustin-Miller family. We can see. So, multi-read question whether all the 7 by 12 resolution are from the Kustin-Miller family. So we answer this question that we use the resolution grade 3 perfect ideal. So this is my joint work with Salikbas, Kreskevich, and Weiman. We define a new family of grade 3 perfect ideal with 5 generators of type 2. This family is associated with a Dinking format E6, like the almost complete intersection. In that case, it is associated with a Dinking format Dn plus 3. Here, this family is associated with Dinking format, Dinking type E6. So in this case, so here we, so in my joint work with Salikbas and Weiman, we constructed doubling of such resolution 1562, and this gave a resolution for of the grade 4 Gorenstein ideal of the form 171271. And in this case, we found that only one Spinor coordinate is among the minimal generating set of the ideal, and all other Spinor coordinates are the linear combination of minimal generating set of the ideal. So here, so this family 1562 has also one more nice property, is that the Tor algebra multiplication is trivial in this case. So which is different from the what almost complete intersection, and the behavior here for the Spinor coordinates also different. So this doubling of 1562 is not a specialization of resolution of the format 171271 given by Kustin-Miller. This argument we saw by the by number of minimal generating set among the Spinor coordinates, but because in case of 7 generator, grade 4 Gorenstein ideal, which comes from the Kustin-Miller construction, has 4 minimal generators which are among the Spinor coordinate. In case of this doubling of 1562, only one of the minimal generator is among the Spinor coordinates. So this gives a new family of the new family of grade 4 Gorenstein ideal, which comes from 7 by 12 matrix, which is not specialization of the Kustin-Miller. So next is we have one more example which is for the grade 4 Gorenstein with the 8 generator. So in this case, here this doubling is constructed using the almost complete intersection coming from 1, 4, 7, 4, and in this case, and this is also almost complete intersection. In this case, it can be found that 4 Spinor coordinate, 4 minimal generators among the Spinor coordinates. So up to the 8, and also up to 8 generator, we have seen at least one the Spinor coordinate is among the minimal generators of the ideal. Sorry, at least yeah. So one more thing is that the behavior of the up to 8 generator and the bigger generator is different. Even in the 9 generator, what we have discussed 19691, That also comes from doubling. I'm not mentioned here. That also comes from doubling of what we call a 1683. That is some Egan-Northcott complex. But the difference, this doubling also differentiate the grade 4 Gorenstein ideal with the 8 generator and above, because up to 8 generators, they all are doublings coming from certain dinking types. Weyman in his work, he has associated every grade 3 perfect ideal resolution with certain diagrams, and so he has associated some resolution coming from dinking format. So up to 8 generator come from the dinking format, like we have seen 1271 come from either dn plus 3 or e6. Even the 11661 that comes from hyperplane section of Pfaffian, that is associated with dinking format an. So, but if we talk about 19691, that doesn't come from the doubling of any grade 3 perfect ideal, which is associated with any dinking format. So, summarizing all the what we have discussed earlier. So we have seen that all the 4, 6, 7, and 8 generators either they are doublings or a deformation of doublings of perfect ideal of codimension 3. I can say 9 generators also. All the known examples are either doubling or deformation of doubling of grade 3 perfect ideals. We have seen all the examples where Spinor coordinates are in the ideal. So we have seen all the examples only where ideals were radical ideal. Also, one more thing is that for up to 4, 6, 7, and 8 generators, at least one of the Spinor coordinates were among the minimal generators of the ideal. But for the 9 generator, which comes from the Gulliksen-Negard, which we call as Gulliksen-Negard complex, in that case, none of the Spinor coordinates were among the minimal generating set of the ideal. So either this Spinor coordinates or this doubling classifies the Gorenstein ideal with up to 8 generator and above. So yeah, these are my references. Thank you.
Yeah, thank you very much, Laxmi, for this very interesting talk. We will take some questions now. You can open your audio and video and ask your questions. I'm Jayalakshmi. I'm curious to know what are some general results for higher codimension. Codimension 4 seems very involved. There are so many families of examples and so many different techniques are used. So are there general results in higher codimension to construct some families of Gorenstein ideals, besides, of course, complete intersections and many determinative ideals are Gorenstein?
So I don't know that, because for the for codimension 3, 4, most of them come from the grade 3 ideals, and that has nice multiplication, associative multiplication, everything. That has nice structure. But for higher, yeah, I don't know. I don't think there is any except this complete intersection and everything. Yeah, I think for the higher. Higher grade.
Okay. And you did mention that there are two Dinkin diagrams, DN and EN, which are useful in these constructions. But there are other Dinkin diagrams we know about classification of semi-simple D algebras. Do they also show up in some constructions?
So for grade 3, for the grade 3 perfect ideal, there's something called construction of generic rings. So in that case, we get generic rings to be Noetherian. There are only certain dinking diagrams which can give Noetherian rings. So either it is E6, E7, or E8, or DN, or AN. These gives Noetherian rings if we construction of generic Noetherian rings. Yeah, so there are perfect ideal associated with the digging type E7 and E8 also. which is not completely determined. The generic construction is not done. Even for E6, it is not done completely. We have the family of ideals, and we associate with the thinking type E6. So.
Okay. Thank you. Thank you very much.
Thank you.
Yeah. Are there other questions?
So I have one small question. Is inverse system useful in constructing a resolution?
Yeah, in case of R-Team, I think there is some work for the doublings. I think Oana, Velice, and Pedro, they are doing some work for using the, I think, yeah, for the R-Team case. So maybe inverse system might be useful.
So Artinian codimension.
For the codimension 4, yeah.
Codimension
we can say
4.
grade 4, yeah. Grade
4. Okay. Yeah, thanks.
All right. Are there any other questions for Laxmi? Okay, so I don't see further questions. So let us all thank Laxmi for her very interesting talk.
Thank you.
Yeah. So, thank you all for attending the talk, and we will meet next Friday. Thank you very much.